Hi everyone, welcome to my channel. I've been experimenting with 8-bit shift registers, and I built a circuit here that I hooked up to my Arduino Uno, but then I thought it would be better just to focus in on the shift register itself, on the 8-bit shift register, and how it functions, how it works, and I could utilize my Heathkit Digital Experimenter to do that, where here I can manually apply signals and exercise how the 8-bit shift register works without it having hooked up directly right off the bat to the Arduino Uno, which I'll do a video on later. But here's a circuit that I have hooked up already to my Heathkit Digital Design Experimenter, and I'll be able to manually apply the clock signals and the data signals. So this way we can focus in on how the chip itself functions before we delve into programming the Arduino to control the 8-bit shift register. So let's get started. So let's take a look at the chip itself. So this particular device here is in a 16-pin DIP or dual inline package. Makes it easy to insert into the breadboard. You can see here the leads on it. And it's 16 pins. And it starts, number 1 is right here. You start with this notch, that's number 1. Count down to number 8 here, and then you jump over, that's 9. And then you go up along here to pin 16, opposite pin 1. And you can see this is an SN74HC595. This is an 8-bit shift register with 3 state output registers. So let's take a look at the data sheet. So here's the data sheet. You can see here this one is an SN74HC595. Here's the particular picture of the 16-pin device that I have, and it identifies each pin. And if you read in here, it tells you what each pin does. And here it says HC595 device contains an 8-bit serial input parallel out shift register that feeds an 8-bit D-type storage register. The storage register has parallel 3-state outputs. Separate clocks are provided for both the shift and the storage register. The shift register has a direct override clear input and serial input, serial outputs for cascading. When the output enable input is high, the outputs are in a high impedance state. Both the shift register clock and storage register clock are positive edge triggered. If both clocks are connected together, the shift register always is 1 clock pulse ahead of the storage register. And the rest of the data sheet gives you all the electrical characteristics. Here's a block diagram of the inside of the chip, and you can see here this is the shift register. Data will be shifted 1 bit at a time into these 8 registers, and then with a clock pulse all 8 at one time can be shifted into this 8-bit storage register. And then you have another control where then you can either simultaneously have that data available to the outside world, or you can wait and then send a control signal or clock to then have it available. Here's some timing diagrams and the electrical characteristics. So let's go over what each pin does, what the function of each pin is on this 16-pin device. So we start with powering the device, and what we have is VCC is the plus supply volts, plus 5 volts to pin 16, and we have the ground at pin 8. So again, this is an 8-bit shift register. So you shift 8 bits of binary data at a time into this chip, and that's what pin 14 is for. Pin 14 is the serial input. So this is where you connect your data line to input your binary data, shift it 1 bit at a time into the shift registers. And this is synchronous, so it's synchronized with the clock signal. And here we have on pin 11, we have the shift register clock. And the binary information gets shifted on the positive going edge of the clock cycle. So if there was a line over this, it would be negative triggered, but this is positive triggered. So every time we get a clock pulse, we can enter in 1 bit of information into the shift register. And then on the next clock pulse, that first bit is shifted and gives us the ability to then enter in another bit of binary information, or 1 bit. Now once we have 8 bits of information, those 8 bits all at once can then be shifted into an 8-bit storage register all at once. So it's a parallel transfer. Pin 14 is we enter the binary information serially, 1 bit at a time. Once we have 8 bits of information, they then all at once can be shifted into an 8-bit storage register. And pin 12 is the register clock for that storage register. So every time there's a positive pulse on pin 12, those 8 bits of information that are in the shift register are then shifted or then transferred parallel over into an 8-bit storage register. There are also 2 other functions, or 2 other pins here. We have an output enable. So pin 13 is an output enable, and this is an active low. So once the 8 bits of information are in the storage register, if you have a low on pin 13, that information is immediately available to the output pins, which we'll look at in a second. But if we tie this high, or there is a high on pin 13, that information in the storage register is not made available to the outside pins yet. Another option that we have is pin 10, which is the shift register clear function. And again, this is an active low. So when we have a low applied to pin 10, we can completely clear any data that's in the shift registers. The remaining pins are how we gain access to the 8 bits of information that's stored in the storage register. So QA, it would be the least significant bit. That's pin 15, and then we have QB, C, D, E, F, G, and H. Those are the output pins. So let's go over the basic operation of this 8-bit shift register with serial input to parallel output. So we have 8 storage locations or registers. And if we can look at it pictorially or block diagram wise, you have 8 storage locations. And there's 8. So we've got 1, 2, 3, 4, 5, 6, 7, 8 shift registers that allow us to store either a 1 or a 0. And we have an input. And that input is pin 14. And that's the serial input to the shift register. and that's timed with a clock signal. So we have another signal, a clock signal, that's the input of this data is synchronized to. So we have this square wave, and every time we have a positive pulse, so on the leading edge, when we go from 0 to a positive signal, that's when we're able to shift a bit, either a 0 or a 1, into one of these registers. So on the first clock pulse, say we want to put a 1 in here. So we send a 1. You know, we have representation of plus 5 volts for a 1 into this first shift register. Then when the clock goes to 0 again, we wait until the next clock cycle or the next clock pulse. We can shift another bit of information into the next register or into the shift register. But what happens is this 1 will get shifted into here, and then the new information will be shifted back into the first register. So if the second bit was a 0, this here would not be the 1, this would be the new information, which would be the 0, and the 1 got shifted over. So if we had 8 bits, see 1, 2, 3, 4, 5, 6, 7, 8, we'd have to have 8 of these clock pulses to get those 8 bits of information into the shift registers. So after 8 clock pulses, we would have 1, 0, 1, 0, 1, 1, 0, 1. Now that's the information that's just in the 8-bit shift register. There is another register called the storage register, which is just like this 8-bit shift register right next to it. So here there's another 8-bit register, but this is called a storage register. And with the shift register, we had a serial input 1 bit at a time, shift it, and it took 8 clock pulses, 8 of these clock pulses, to get this 8-bit of information into this register. Well, now we're going to do a parallel transfer, which is going to take just 1 clock pulse. And in 1 clock pulse, we're going to shift this information out from the shift register into the storage register. So let me clean this up now so I can then show you the outputs. So this is the status of the 2 registers once the register clock pulses and transfers all the binary information that's in the shift register all at once into the storage register. And QA through QH are the 8 outputs that are made available all at once. So we have serial data in and parallel data out. So the 8 bits are simultaneously made available to the outside world. Now we do have that control line, which is pin 13, which is output enable, OE, and that was an active low. So if you tie that pin to ground, as soon as the register clock pulse transfers the data from your shift register to the storage register. It'll then be available to the outside world through these pins QA through QH. If you have this at 5 volts, you then have the ability to then still further store the binary data in the storage register until a point in time you want it to be available to the outside world. That you would go from +5 to 0 volts, and then this information would be available to those pins that supply QA to QH. Now, another pin of interest is pin 9, which is QH, I guess prime, I guess. So what happens if I shift another bit of information in here and shift these bits over one more bit? Well, this one just gets lost. But what you have is pin 9, which allows you to connect pin 9 to the serial pin of a second 8-bit shift register. So you're able to cascade these, and then you would be able to control 16 outputs. So now let's go look at the operation of a shift register with the help of the Heathkit Digital Design Experimenter. We can manually apply data and clock signals and shift data into and out of the 8-bit shift register. So here's the circuit I've got wired up with the 8-bit shift register, the 74HC595. I initially was just going to use these 4 LEDs to show how data is entered into the shift register. And the designer already has the current limiting resistors built into the board to light these LEDs, but I decided to go ahead and add the remaining 4 LEDs so we can see the full functioning 8-bit shift register. So I've got the current limiting resistors right here. Now here, this is going to be my data input switch. So when it's down, that simulates a 0, and when it's up, there'll be 5 volts available here. So 0 and 5 volts. So these switches here are going to simulate my shift register clock and my storage register clock. And they normally have, they're normally A naught. So there's a 5 volts normally on A naught and B naught. This is a momentary switch, spring loaded. So when I switch it to A momentarily and release it momentarily, there'll be 5 volts. So this will simulate a 5 volt pulse or clock signal. And the same here for the storage register. So when I pulse the storage register, the information or the data, the binary information that's in the shift registers will be transferred to the storage registers. And since I have my output enabled tied to ground, that information will immediately be available to light these LEDs. So I have my meter here hooked up to one of the clock signals. This is the shift register clock, and you'll see that when I move the switch to A, I will then have 5 volts. So you can see there, I have 5 volts, and then I release it, and we're down to 0. So that's going to simulate a clock pulse. So using the shift register clock in conjunction with the serial data input, whether it's going to be a 0 or a 1, simulating a 0 or a 1 as the data, I'll be able to clock in 1 bit at a time, either a 1 or a 0, and fill each of these 8-bit shift registers here. I also decided to hook up the shift register clear so I can show you that when we apply the shift register clear is an active low. So if we leave it on high, it has no effect, but when we go low, and then clock the storage register, it'll clear all the information in those registers. So let's go ahead and enter some data, and hopefully that'll give you a better idea of how the 8-bit shift register works or functions. Okay, so since I already have this as an example, let me go ahead and enter these bits in the order that we used in this explanation here. So we're going to start by entering a 1, and then a 0, 1, 1, 0, 1, 0, 1. Remember, this is going to be the first bit of information that gets shifted as it starts at this end and slowly works its way down to this end. So this is the data switch. So if we look at that switch in the current position, you can see that there's 5 volts on that. And when I go to this position here, there's 0. So that 5 volts simulates a 1. That represents a 1 in digital binary information. So we have a 1 being applied to the serial input to pin 14 on the chip, and now I have to clock that data in. And I use this shift register clock to shift that information. Now we're not going to see any LEDs light up until I apply my storage register clock. So that just shifted in a 1. And the next bit I want to shift in, I have to change to 0. So I switch to 0, and then I clock in that bit. So for right now, let me show you that I in fact do have those 2 bits of information stored. I'll make them available to the outside world by clocking the storage register. Remember, I have the output enabled, active low tied to ground, so as soon as I clock with my storage register clock, it'll light up at least the first. Remember, I entered a 1 first and then a 0. So this will be a 1. This will light up. This will be a 1, indicating a 1, but this will stay unlit. But that indicates that, in fact, a 0 was entered. So let me go ahead and clock the storage register. And there you go. I have a 1. So I have a 0 and a 1 that I've entered so far into the shift register. So now I want to add another 1. So there's a 1 for the serial input. The data is a 1. And then I can go ahead, shift that into the register, into the shift register, and I can see it if I go ahead and clock the storage register to make that available to the outside world. Remember, this gets shifted over to the next register. The 0 gets shifted over to the next register, and then this LED will light, indicating there is a 1 now in this register, so it's 1, 0, 1. So let me go ahead, clock it, and there you go. I've got a 1, a 0, and a 1. Now I want to shift in another 1. So shift in another 1, and then I'm going to go ahead and pulse the storage register clock. Now I have a 1, 1, 0, 1, and everything's getting shifted into the registers. So now I want to add a 0, so there's a 0. I clock that into the shift register, and let's take a look. And now I'm down here because I only had 4 LEDs. I added the other 4 here. So I've got the 0, 1, 1, 0, 1. And now I want to add a 1. So there's the 1. Shift that in. And then I can pulse that storage clock again. And now I have a 1, 0, 1, 1, 0, 1. I want a 0. Shift that in. Pulse it. And then I want a 1. So this goes up to 1 again. I shift that in. And there we go. So here I have, if you look here, right? 1, 0, 1, 0. The first 4 here. 1, 0, 1, 0. And then I have 1, 1, 0, 1. 1, 1, 0, 1. And that's correct. Now, as far as which is the most significant bit and the least significant bit, I guess at this stage it would be open to interpretation and how you would interpret that programming-wise. But this bit here was the first bit that we entered. So this could become this is the least significant bit, and the last bit could be the most significant bit, or vice versa, I guess, depending on how you interpret that with support circuitry or programming on the programming side. I don't think it's a given that it has to be one or the other. Now, I didn't have to clock the storage register each time I entered a bit of information. I can enter in those 8 bits and then make them all available to the outside world with one clock pulse. Now at this stage, let me show you now that I can use the shift register clear function here. So this is an active low, so I have it tied high right now. It's 5 volts on there. So if I go low, and then I pulse the storage register clock, it'll clear out all the binary information out of the registers. So here we go. So there we go. I've cleared all the binary information now. There's zeros stored in all the registers. So now I can pull this up high again. So here's an example of shifting in 8 bits of information using 8 clock pulses for the shift register clock. And I'll just leave the data input on high, so that will represent a 1 that we will store in each of the 8 registers, and it's going to require 8 pulses for the shift register clock. So this, again, this is a 1, and I've now shifted in a 1 into the first register, and then on the next clock pulse that 1 will shift into the second register, and then a new binary 1 will shift in to that first register. So that was 1, that's 2, and just repeat it, 3, 4, 5, 6, 7, 8. And now when I pulse the storage register clock, all 8 bits will become available to the outside world, and those were all 1s, so all the LEDs should light up. So let's pulse it, and then there they are. So those represent a binary 1 on each of the outputs. And again, I can clear it with this shift register clear. So go to 0 and then clock 1 pulse with the storage register, and I've just cleared all that data. And that's the basic operation of an 8-bit shift register. So that's how an 8-bit shift register works. I hope this experiment utilizing the Heathkit Digital Design Experimenter has given you a little bit of insight and understanding of how the shift register works, how you hook it up, how you input serial data, and then how that data is output in parallel. And hopefully this information will help you understand a little bit better how we go about hooking up the shift register to the Arduino Uno in the next video, and how we're able to get it to function and work. So if you like this video, feel free to subscribe, like, and/or comment, and thanks for watching.